already looked at that. First of all, it's only males. Secondly, it's only 9 of them, which means potential for wide noise in the study. A lot of noise possibility. Low power, to use those words again. We can set the confidence, but the power is going to be super low because of this. We'll come back to that again. But what I want to do is I want to look at this results. I want to look at this results bit right here, because that's the part I really want to focus on today and Tuesday, is what these symbols mean. This is a huge part of 244. I've inserted this section into 244 because I realized that I used to do it with other stuff and it got lost in the wash. This idea of what are called p-values. We're going to get into that today. So caffeine, it sounds like what they had was they had 3 groups, or they had each dude tested 3 times in double-blind fashion. They got a pill, and then they put them on a bike, and they made them do their cycling thing. 60 watts, 100 watts, 90 watts, whatever it was. And they each got a pill, but they didn't know what pill they were getting. Some of them got a placebo. Some of them got a pill that had nothing in it except placebo-y stuff. Some of them got a 1.5 milligrams per kilogram of body weight caffeine, and some folks got 3 milligrams per kilogram of caffeine. And I'm assuming that it was randomized so that it didn't go like 0, 1.53. 0, 1.53. I'm assuming that some of them got the 3 first, followed by the 1.5 after it had a chance to flush out of their systems. Does that make sense? And that's why I had you guys flipping coins in class yesterday with the touch therapy experiment, because you wanted to randomize what you were the experimental variable. They were significantly lowered by a range of 4 to 7 BPM. Don't worry about that because that's not important for us right now. But it lowered it compared to placebo during submaximal exercises, but it didn't lower it when they were at rest or at maximal exercises. Strange terms. At rest for a cyclist means something different than at rest for a normal person. At rest for cyclists, like for me, I'm spinning along on flat ground, having a great time going about 21 miles an hour. I'm completely at rest. I'm expending almost no energy. I'm wickedly efficient. I'm down. Submaximal means I shift up a couple gears, most likely. Maybe the grade goes up a smidge, and I start mashing. But I'm not mashing to the point where my legs are burning from lactic acid yet. I'm getting right below that level. And that's a cyclist in your case. You're a cyclist, right? I thought you were for some reason. You got any cyclists? Okay, so maybe I'm speaking French and I apologize. And then maximal, you've seen Tour de France riders when they're maximally racing. I mean, they're all out. They're looking down for more gears. They don't have them, and they might be burning through their lactic thresholds. I don't know. But what this study found was, if we're in that sub-max range, caffeine's going to lower your heart rate. How surprising is that? Not only is it caffeine, but you're also kind of kicking ass. Your heart rate should be going up, but all of a sudden it does something unexpected. That's why I like this study so much. It caught my attention because of that. See my surprise? Or maybe you're kind of scratching your heads too, going, that doesn't make any sense. Good, it doesn't make any sense. There's no sense. It should go up, not down. Good. Okay, so I want to break some terms out of this first. Break some terms out. There are hypotheses being tested here, without being verbally called hypotheses in the article. Very often they don't say words like null, research, hypothesis in the articles. They're just one of those things that, much like when you listen to a drummer playing drums, you won't hear him say, I'm going to play a paradiddle now. He just does it. And it sounds wonderful. Or she just does it, and it sounds wonderful. So the research hypothesis is what you're testing. It's what you want to be true. It's what you want to be true. So in this case, when these people wrote this article, they wanted the heart rates to go down. In this particular, during certain levels of exercise, submaximal in this case. The null hypothesis, this is the one we were talking about earlier, is what you go in assuming. It's easier to assume the null. It's easier to assume that caffeine will not lower heart rate. That makes sense, I think, right? It's easy to assume that, because we drink coffee in the morning not to lower our heart rate, to wake the hell up for the day. So it's easy to go in there and say, you know what, caffeine's not going to lower heart rate. That's a stupid idea. Is anybody wondering why they even tested this idea? Why would you go in and spend money to test if caffeine would lower heart rate? And you have any ideas?
To see if you should put it in the energy drink.
But why? Yeah, but why? Very good. Why caffeine? Why not something like, oh, I don't know, what's creatine? Why not use creatine instead of caffeine? It seems equally kind of off the wall, right? I love what you're saying, Elizabeth, to see if we should put it in like supplements, but why caffeine? Where would that come from?
Our love of coffee?
You know what? Actually, yeah. I would bet that I got this theory, and I haven't been able to contact the authors of the article to ask them, but I got this theory that a bunch of dudes, after a bike ride, were talking about, you know, I started drinking a cup of coffee before this hammer session. You know, I can totally kick your ass on the hills. No, I don't believe it. And then somebody else down in an espresso or something, or a cappuccino, and they're like, oh, dude, it totally works. Now, you run the risk of that. Years ago, somebody told me that circus peanuts had the exact same effect as Cliff Bars. Or Cliff Bars weren't around at this point, it was Power Bars. I'm like, holy crap, that's genius. So I bought a bunch of circus peanuts, started packing those in my as it turns out, there was an article written in the April 1st issue of Dirt Rag. I totally missed the April Fool's joke. Circus peanuts, this is friggin' awesome. I'm like down these on rides, I'm like, kick your ass, and I'm beating her at the hills. Complete placebo. Complete placebo effect, right? Complete placebo effect. That's why you can take the anecdotal kind of experience and apply a test to see if it's just anecdote or if once you control it in a controlled setting, if it's replicable. Like, oh yeah, dude, by the way, the reason you're kicking your friend's butts up the hill is because your heart rate's lower, you're conserving energy, and you can kick his ass on a longer climb. I mean, that's what these studies are born out of. Usually they're born out of anecdote. That's kind of badass, right? They're born out of anecdote, and it becomes scientific, if you will, fact, quote unquote, once you can submit it to rigorous testing. Is that believable? I often wonder where these ideas come from, right? How does red food dye get associated with ADHD? Well, because parents are like, dude, don't give your kids strawberry ice cream. You're going to come back, the babysitter's going to be drunk, the kid's going to be passed out naked on the floor. If you hear that enough, or something like that, enough, you start going, I wonder if there's a connection. And that's where the wonderment, the anecdote, turns into this, and turns into these, and turns into a conclusion. Does that make sense? I don't want you to think these studies fall out of the sky like done, or the ideas fall out of the sky. They come from experience. They come from that kind of thing. Beautiful. So in this case, we have a research hypothesis. It's that caffeine is going to lower heart rate somewhere. That doesn't make any sense, because you don't know how much, you have no idea why it would. So you go in assuming it's not, which is very easy to support anecdotally. Yeah, because caffeine's a stimulant. This is what we set up, and this is what the rest of the course is going to be, is developing these tests as we go. That's what we're doing together as we go. Okay, so we had the mention of the word placebo. I've used it a couple times today as well. I mentioned the placebo effect by circus peanuts. I'm sure it happens quite a bit. I've often been told I go to acupuncture for my allergies. And my friends who are very scientific goes, I can't believe you go to acupuncture. I'm like, it works. Like, how you like that placebo? I'm like, if it works for me, why is that a placebo? They're like, you're a statistician. I'm like, I don't care about statistics here. I care about anecdote. And it works. And they're like, ah, that's a good point. Statistics is not the be-all and end-all. Statistics works, 244 works, when you are interested in testing the average of a population. When you are interested in coming together with something that will apply to a population. If all you care about is if something works for you, you throw away 244 and you do what works for you. Huh? You're a sample size of 1. That's anecdote. That's not statistics anymore. Is that fair? So if you take airborne for a cold, because airborne works for you, that's awesome. It doesn't work for the general population, but it works for you. You see why that's important? Statistics is not the be-all and end-all. I'm here to tell you that today. It works for a population. If you're interested in curing polio, or if you're interested in researching whether or not caffeine will do this in all bike riders, or if green tea affects breast cancer rates, or if red wine affects heart attack rates. If you drink red wine because if you think it makes your heart better, that's you. That's anecdote. You don't need tools for that. Did everybody see the difference here? Okay, good. Good. Thank you. Thank you. Thank you. Thank you. So anyway, a placebo is something that you mix in to make sure your research subjects are unknowingly getting nothing. You're trying to remove bias in this way. I think I've told you about the power bracelet study, right? The power bracelet study? No, I haven't? Okay, so power bracelet, you see these energy bracelets, right? Put the energy bracelet on. I thought the performance improves exponentially. And there's a great YouTube video I found years ago. It's gone now, unfortunately. But it's this dude in the gym go, dude, jump! And this little guy goes, okay, and he jumps. And then he comes back, he's like, dude, now put the energy bracelet on, it's gonna make you jump further. Puts it on, he jumps like 3 feet more. It's like, you see? I'm like, see what? You see how energy bracelet makes you jump further? I'm like, I see that he got a warm-up trial to see what a jump felt like. Then he did it a second time. So he's gonna jump further. And I see that you're yelling at him to jump further, so he's going to jump further. Plus you're in one of those shirts. Ripped. So that's what I see. What I don't see is this kind of an experiment done, although you will see it soon. It's published, I think, in 6 months. I keep begging the guy for the data. A dude took the same energy bracelet data, or he took energy bracelets and made fake ones. He made placebo energy bracelets that looked exactly like the real thing, even with like the insertion of the copper band, or whatever the hell's in those things. And he put people in the jump test, but he didn't tell them, he was putting a bracelet on them every time. So all they knew was they were getting a bracelet and then they were jumping. And guess he was flipping a coin to decide which bracelet they got first. And he'd do the average length of a jump with the placebo and an average length of a jump with the energy bracelet. No surprise, what happened?
No difference.
Nothing, two intervals stacked on top of each other, essentially. Now he hasn't published his data, I can't wait to see it, it's going to be fun to talk about in class. But nonetheless, no difference. No difference, it sits there. So that's why you're trying to remove, the placebo is trying to remove bias. You're getting a pill. So you're taking a supplement, but you don't know what you're getting. So hopefully not knowing what you're getting is offsetting any, oh, that's going to be caffeine. So that's why they have to give them something. The placebo just can't be not receiving a pill, because then if you receive the pill, you know you're getting something. Does that make sense? A lot of times they call it sugar pill. Sugar pill. I guess they put sugar. Although it seems like a sugar pill would also be a confounding variable by having sugar in it, but whatever. What do I know? So anyway, your experimental group is going to be getting the caffeine, the caffeine levels, and the control group is going to be getting the sugar pill, the placebo pill. Many times, the control and experimental groups are the same group. It's the same people. In a study this small, it's going to have to be with 9 people. This way you can get 27 data points, because you test each one of them 3 times, assuming you wait long enough to flush out all the toxins and the caffeine, which you can. That's what, assuming your liver's working. That's what it does. Cool so far? You guys buy this? All right, let's keep going. We've been through this many, many times. Often you'll hear me say, assume the null, which sounds like Latin. That's when you go into a study, you say, nah, caffeine's not going to do anything. That's the null hypothesis, that caffeine's not going to do anything. And then you're surprised when caffeine does do something. But the null hypothesis is that caffeine is not going to do anything. Is that okay so far? Good. All right, so now I want to talk about these. This is my favorite part of this day and also Tuesday, is talking about those big P's. They're called p-values. Some of you have seen them before in research articles. Some of you have seen them. Very often you see them paired with the number 0.05, which is 5%. And you might have an idea of why they're paired with 5%. Any guesses?
95% confidence.
Because you're tied to a 95% confidence interval. This is the number outside that confidence interval. So you've got this interval that you've drawn around a statistic, and then you've got the exit region, or the critical region, or the false positive region, 5%.
Isn't that also the rare example?
It's all tied back to that, yeah. I don't even talk about that in 243 because it makes a lot more sense now, but yes, that's exactly what it is. You got it, you got it. So what it is it's a conditional probability. And you might not remember this from 243, and that's okay. A conditional probability has a vertical line, which means given that. So, or assuming that. So assuming that the null hypothesis is true, assuming the null hypothesis is true, what's the chance that we got the data that we did in our experiment? Mathematically, let's measure that probability. Assuming the null hypothesis is true. That's what we're going to spend the next six and a half weeks doing together, or 6 weeks doing together, is measuring those probabilities. Now, what I did here was, and we're going to do this over and over again over the next day, is tie that general probability up to the actual experiment. So in this case, we're going to go ahead and assume that caffeine has no effect on lowering heart rate. Because why the hell would it, right? Why the hell would it? It's caffeine. So we're going to assume it's not. But then what happened in our experiment? Holy crap. The heart rate was lowered when they had caffeine. That's surprising, isn't it? That's a surprise. We're surprised because the thing that we were assuming over on this side disagrees with the data that came out of our experiment. Do you see that kind of butting heads? We call that a contradiction mathematically. You're assuming one thing and then something comes along and smacks your blind side. That's a mathematical contradiction. You sit back and you go, now Brandon's going to say, why? Good for you. But just the fact that it happened as a contradiction is what catches our attention. With me so far? With me so far? Okay, good, good, good. So what I want to do is I want to look at this graphically now. This is where it gets. This is where I think it gets fun. I think. I could be wrong. This is where I think it gets visual, so it gets more believable. Here is a number line on which, see, Quincy, let's stop it. On which is heart rate numbers. What's this right here? Say it again. Average heart rate. Thank you, Brian. I didn't mean what number it is because I've hidden all the numbers. I don't want you to know what the numbers right now. So it's the average. You guys see this on your slides, on your pages? Sorry, I'm flip-flopping back and forth between the single handout and then the PowerPoint slides. We're just going through these kind of quickly. That's why I wanted to give them to you to make sure you could follow along if you wanted to. That way you're not scribbling down notes constantly. So this is average. Is this better? It just got darker outside. It just got rain again. Yay. Maybe this means it's snowing up in the mountains. Yes. So here's average, yes? I don't know what average is, but it's average. Whatever it is measured as average. And that would be the average heart rate, right, of somebody at sub-max workout. So, you know, I mentioned before, that's when I'm cooking along. Maybe the angle's up a little bit on the road, and I'm starting to mash in because I'm gonna get my heart rate up a little bit. But even though I've got my heart rate up a little bit, it still has an average at that level, right? It might be that it's 42 beats a minute at rest, 60 or at sleeping, 60 beats a minute at rest. Maybe it goes up to 80 beats a minute sub-max, but it's got an average. And the population has an average measurable. And clearly, if I go this way, the heart rate goes up. So, do you believe that if we give somebody caffeine, and we believe that caffeine is not going to lower heart rate, we think they should either land here or this way? Does that make sense? We're giving them caffeine. We assume caffeine is not lowering heart rate. We predict, therefore, that they're going to land here or here, because that's what happens without caffeine. So why would caffeine make it go anywhere besides that? Is that fair? Status quo? Well, the problem is, this is where the data landed. They gave these guys caffeine, made them work out sub-maximally, and they didn't land here. And they didn't land here. They landed down here. Now, why did I color this red? How much area is down here? Take a guess. Yes! Because what is this green or gray, whatever color it is? That's your 95% confidence interval for the heart rates of sub-max folks who aren't using caffeine. Okay? That's the normal confidence interval for those not using caffeine. What you just saw was, you just saw the fish jump out of a tank. You expected the fish to be in this tank, right? You expected two parallel tanks. Heart rate without caffeine, heart rate with caffeine. And all of a sudden this damn fish comes in and goes, boop, boop, over here. And you sit up and take notice and go, holy crap. Caffeine just lowered their heart rate from where it should have been. And then as a bicyclist you get excited because you're like, well, this is great. Because now I can go and I can work harder, or I can pedal faster and then get my heart rate. I can get my heart rate back in here, but I can pedal faster and go faster and kick his butt. But the important thing is that it did land here. Is that fair? Do you guys buy that? So that makes you sit up and take notice, because it shouldn't have happened. What do we call something in statistics that shouldn't have happened? It's an outlier. It's an outlier. We like outliers in 244. This is why I was so confused in 243. The textbooks keep taking out formal study of outliers. I keep putting it back in. You need to talk about outliers. And I also want to make sure we don't always throw outliers away. Right? An outlier isn't always a bad thing. It could be a bad measurement. This could be a bad measurement for that matter. And an outlier could just be random fluctuation, but sometimes outliers tell you something else. Sometimes they tell you something else. Like this. This might tell you something else. It might tell you that caffeine is lowering heart rate. It might be it was a fluke. Maybe the heart rate is still exactly what it's supposed to be and we just happen to catch down here. How often is that going to happen? How often is that going to happen? Out of 20 times. About?
1.
Good! About 1 in 20 trials. Even if caffeine isn't lowering heart rates, you're going to land down on that tail about 1 in 20 trials, aren't you? Is anybody pissed off that this confidence interval is not two-sided? Did anybody catch that? You guys very clearly said this was 5% and this was 95%. Does that upset anybody? That it's not 95, 2.5, and 2.5? It's okay. You can have one-sided intervals too. Your TI can't build them, but they are completely legit. You use one-sided intervals if you're trying to show that something cannot go in one direction. Sometimes you want to know if it can't go in two directions, or if you're trying to estimate a parameter, because you're not sure which way it's going to go. But if you have a theory that it's going to lower or raise, you only want to go in one direction. So good. If you're upset about that, don't worry. The key is not so much the one or two sides at this point. The key is how much area it traps, 95%. That's the big takeaway. Fair so far? Good, good. So here it is. Here it is in words or in symbols. What is the chance, assuming that caffeine had no lowering effect on heart rate during submax exercise? That's a mouthful, isn't it? The chance, assuming that caffeine is not going to lower your heart rate, what's the chance it actually did? Well, that's a contradiction, right? It's an outlier, right? That means it should be very unlikely, less than 5% of the time, because it landed in that region. It should only happen at most 5% of the time, preferably a lot less. Those of you guys that have seen these p-values in the research, have you ever seen it like when it's less than 0.001 or 0.00001? Or they just go ahead and say it's equal to 0. Sometimes they do that too. Bastards, they shouldn't do that, but they do sometimes. Yeah, they're trying to drive home the point that what we saw was exceptionally unusual. This is unusual. If you're assuming that caffeine has no effect on lowering, but the data comes back and shows that it's lowered, you scratch your head and you start wondering why. Is that fair? Is that believable? You guys, ask me questions if you have it. I always worry about this being too much preach, not enough back and forth.
What about the
yes.
other...
What about the other ones, Aaron? Thank you. Let's look at them. Thank you. How about the other two? How about the at-rest and the maximal exercises, right? So I put them both on one graph. Thank you for this question. I put them both on one graph if it's okay. So here are normal average heart rates, elevated heart rates. And this could be either during a maximum workout or at rest. The bell curves won't be in the same place. At rest will definitely be shifted down here and max up. But the idea is when you checked the athlete's heart rates, when you check their heart rates at rest and at maximal with caffeine in their system, this is where they landed. Well, that's where you thought they should have landed, right? If caffeine is not lowering heart rate, they shouldn't land down here. It should land in this lion's share of the area. They should land on this side or this side, maybe up here somewhere. But they sure as hell shouldn't land down here. So that's why, if you look at the writing of those, oh, not at rest, we'll go there. So, once again, the null hypothesis assumes caffeine has no lowering effect on heart rate at rest. And then guess what happened? We took the athletes at rest, gave them caffeine, and their heart rate didn't go down. Are you surprised by that? No, you're not surprised by it. You were expecting that. That's why the probability is high. Bigger than 5% means you're inside the confidence interval. You got a fish that was in the tank. You were expecting a fish in this tank, and the fish is in that tank. No escaping. No escaping. No fish jumping out where you're like, holy crap, where'd he go? He's in the tank. Aaron, does that make sense? Is that believable? Yeah. Same thing happened at max. Same thing happened at max. Right there. Same thing happened during maximal exercise. We were expecting the heart rate to either stay the same or get higher, and it didn't lower, which means it stayed the same or got higher. I don't know exactly where it landed in the study. It doesn't matter. All we know is it didn't get lowered. And to use Chris's word, significantly. It didn't get significantly lowered. Yeah. So that's why it's bigger than 5%. That's why it comes in at bigger than 5%. Because bigger than 5% at 95% confidence means you're 95% confident it didn't get lowered. But when it's less than 5%, you're like, oh, I built this beautiful tank for this fish, and the damn fish doesn't want to swim in it. So then you gotta go find out what tank the fish does swim in. This goes up to Brandon's question. Now I gotta go find the damn other fish tank and see where it lives. But that's like math 245 or 246. But we'll get into that too a little bit in this class. Does that make sense? The big idea, a small p-value means what happened? Good, I love that. It's an outlier. Yes, a small p-value means we witnessed an outlier. So from a research perspective, give me one of two things that could have happened if we saw an outlier. This is good. I like this very much.
And error in how you measure.
Okay, one of three things. Thank you, Brian, for saying something I wasn't expecting. We could have been an error in how we measured. We could have screwed up the measurement. Okay, and I totally appreciate that. That definitely goes without saying. That could have happened. Let's assume we didn't measurement error or anything. I love what you're saying, though. Let's go for only non-sampling error, only sampling error, not non-sampling error. I love what you're saying, though. So, one thing is, okay, here's the sub-max workout, right? Sub-max. We landed down here. It's an outlier. Is it possible that the average heart rate of caffeine cyclists during sub-max workout is still the same average as it was without caffeine? It's possible. Is it possible? Just give you a heads up. Whenever I ask that question to the test, you can always say yes. It's always possible. It's just not probable. See, it's always possible. It's always possible. All right? Is it possible you're going to live forever? Of course, you're Yoda. But it's not probable you're going to live forever, right? I know he died. That's right, he did die. Shit. Ruining my example. It's good though. Very good. It's possible. It's possible. Watch you, I will. It's possible that the average is the same, and we just saw an extreme value. But what is probably more probable? Since that happens so rarely.
That you're gonna land in there.
Well, good, but we landed here. So talk to me about this data point. If it's so unusual to be on this curve,
Everybody reacts different to caffeine. It could have been just some random.
we're assuming, but that's what the margin of error ties in. I love what you're saying. It's not anecdote anymore. Good, it's not anecdote. I love that.
The average is lower.
Maybe the average is lower with caffeine, and there's some other curve that we can't see. Now, we're never going to see it. We're never going to see it. We can see this sampling distribution pretty easily from data. But maybe it's so far away from the center of this curve that there's a secondary caffeine curve that actually indicates that it's lowering. And if that sounds stupid, and it might sound stupid, it's perfect, by the way, Brian, what you said is perfect. Maybe there's a second curve. This is why you guys take Advil for headaches. Because Advil was shown to have a secondary curve for the amount of time it takes to relieve the headache symptom over placebo. This is how the CDC or the FDA tests these drugs. They put them up versus placebo, and they watch the curves. And if the curves separate far enough, they go, boom, even with a margin of error, we can show effectiveness. That's what we're doing here, exactly the same thing. More on that secondary curve on Tuesday. You guys look positively flogged right now. It got dark out, I turned the lights off, it got warm in here, and it's nap
We're
time.
ready for a nap.
Ready for a nap, yes?
Or some caffeine.
So, or some caffeine from some max exercise. So, big takeaway. Big takeaway. When you get small p-values, as a researcher, how do you feel? When you get these small p-values as a researcher, how do you feel?
Happy.
You feel happy, because what you're interested in seeing, you probably just saw. You could be wrong, of course, always. But what you were trying to measure shows an effect. That's why you see small p-values in research all the time. You very rarely see exclusively big p-values, which is a shame. Which is a shame, because big p-values can be wrong too, just like small p-values can be wrong. We'll get more of that on Tuesday. More of that on Tuesday. But you don't read about false negatives as much as you read about false positives. And again, because there's two curves here. I'm only showing you one. So thus far, I'm only showing you one. We'll bring the second one here on Tuesday. Is that cool? You guys have a good weekend, huh? Take care of yourselves. I'll get an in-class quiz for us to play with on Tuesday, too. So we'll keep this idea rolling. Man, it's dark in here. Holy crap. It's wicked.